Hello everyone. In this video we are going to talk about edge bridge, the control for a motor's direction of rotation. So what is exactly an edge bridge? An edge bridge is basically, as I said, a circuit that allows you to turn a DC motor in either way. Because you cannot just go in one way, right? Assume that these DC motors are running your mobile robots. If your robot wants to always go forward, yes, but if you want to back up, then you need to go in the opposite direction. And so if you look at it, basically all it is in simple electronics is a combination of 4 transistor and 4 diodes. That's all it is. 2 of them are PNP and 2 of them are NPN, and there are 4 diodes here in parallel. With each one of them there is a diode, and that is how you put the motor between these transistor junctions or diode junctions and connect it to the high and the low voltage. And this, depending on which one of these 4 transistors is on and which one is off, which one switched on and off, then you can get different directions, or you can stop the motor, you can brake, we call it dynamic brake, and so on. And there are all sorts of different basically edge bridges outside. Some edge bridges are simple chips, okay? So basically they are an electronic chip, and basically they come with some legs, and that's basically all you get. You can easily communicate with that and change the direction of rotation. Now, many times these days you get a driver, you get a motor driver. And the good thing about motor drivers is, first of all, you can control more than one motor. Most of the time you can control 2 motors with that. And not only they allow you to change direction of rotation, they also allow you to apply the PWM, which I showed in my previous video, pulse width modulation. So you can do both of them. You can control direction and the speed, and you can do it for more than one motor, which is very important. As I said, if you have a differential drive robot, you need at least 2 motors. Then you can run the whole thing with one of these drivers. Okay, so in this video, as you can see here, I have a driver, which we're going to talk about it, this guy here. And I do not need any other thing. If you remember in my previous video on PWM, I had to use resistors, I had to use separate transistor, right, and so on, and a bunch of wires to basically apply PWM to one DC motor without even being able to change the direction of it. So this one is a specific thing, and it has all of the things that you need, right? So you see, if you look here on this driver, you can see that there are 4 transistors per motor. So there are a total of 8 transistors. Remember, as I said, each 4 of them goes for 1 motor. So you have 8 transistors. Okay, and there is capacitor here. There are all sorts of electronics to get the job that you want, right? And these are really beautiful, and that they basically cover all of your needs. So what did we do with these transistors? It's very simple. If you look here, if I go ahead and turn on this top left one and the bottom right one, so both of these switches are on, I applied more than enough of voltage. Now in case of PNP, that's different than NPN. But if I turn these 2 switches on and these 2 turn them off, what happens? Well, electricity has to go from high voltage to low voltage through this path. That's the only path that it can go. So now if you look at the motor, the electricity is going from left to right. On the other hand, if I turn these 2 off and turn these 2 on, electricity has to go like this. Now you see you're going from right to left, and clearly going in different directions, as you know, based on electromagnetics. If this is one of the loops of the armature winding, if you go this way or if you go this way, depending, this way. So if you go clockwise or counterclockwise, these different eyes will change the north-south pole. So one of them goes like this, the other one goes like that, okay? Depending on the direction of rotation. and that causes the initial torque to be in the opposite direction, and that is going to cause the rotation to be in the opposite direction. Good. So this is very obvious in how we switch the direction of rotation with 4 transistors, 4 electric switches. Now, one thing important is, why would you use the diodes here, right? What is the role of these diodes? These diodes is what we call kickback diodes, that they are around the motor Y and next to the transistors to protect it from what we call inductive kickback. What is inductive kickback? If you know, the voltage across an inductor is L di over dt. So if the electric current in an armature, which is inside the motor, if it changes all of a sudden, there will be some big voltage created across that inductor. Okay, and that is going to cause a sudden change in the voltage and the current. So there will be, when there is big voltage, there will be big current coming after that, and there will be a sudden spike in your current and voltage, and that can damage the wires of your winding. That is called inductive kickback. Okay, it will be a large spike, as I said, in both voltage and current. So in order to stop that from going back into the motor and damage the winding, what you do is you put these diodes, and as you know, and I will have a separate video on diodes. Diodes are like a one-way valve, correct? Like a pass valve or check valve, you call them. So basically they allow the electricity to go this way, but not the opposite direction. Okay, so if you can see here, when this voltage is created, if it wants to basically go back, right, this is the direction of the flow. But when this voltage is created and it wants to go in this opposite direction and go in the opposite direction of the current and damage the windings, this diode says, hey, I'm not going to let you flow through me, okay? And it is going to kill that inductive, what we call kickback. So these are protective elements from the back currents from the inductive flow or inductive kickback flow. Now, we can also ask why there are 2 PNPs and 2 NPNs, why not all 4 NPNs and all not 4 PNPs. And that I can postpone to the video where I talk about transistors, the difference between PNP and NPN and MOSFET and other things. But just know that on the high side connected to the high voltage, we use PNPs, and PNPs, they turn on when they get a low voltage. And on the low side, we use NPNs, and NPNs will turn on when they get a high voltage on their base, okay? So more discussion of that, why we put them the way it is, I can, again, talk about it in an upcoming video about transistors. So let's postpone that for now, but just know that on the high side, PNPs, on the low side, NPNs, and by switching the 2 that are in front of each other in either direction, I can switch the direction of rotation. Now, you might say, what happens if you turn both of the ones on one side on and both of the ones on the other side off? So both of these on, both of these off, correct? What's going to happen here? Well, in this case, the current, instead of going through the motor, because it cannot go through the motor, both of these paths are closed, it's going to go through this circuit here, okay? And in this case, you basically, as you can see, you found a short circuit, right? Because this circuit here through these 2 transistors on the left does not show much of resistance, so it clearly goes through that. And what happens here is, since, as I said, this path has very, very small resistance, then the voltage is fixed. You're going to get a very large current, and the large current, it is going to destroy some of the components. This scenario, whether it goes completely on the left or completely on the right, we call it the shoot-through current, and it is high and it is going to damage. So you never want to have both the left ones or both the right ones to be on or off. Okay. Now, one other thing is to make sure that if ever that shoot through happens by any accident, so anything happens in this edge bridge that makes both of these on, right? To minimize the damage by the shoot through, what we do, we typically use intentional delays. We call them dead times, and we use them into the switching of the transistors. So when this one turns on, even if this one turns on, it's not going to happen immediately. There will be some delay once the first one is on, this PNP, for the NPN to go on. There will be a dead time between them. So the time that both of them are on, the time that they both overlap and there will be high current is minimized if it happens. So these switches are not perfectly synchronized. There is a little bit delay between them turning on or off. Okay, and that is to avoid any damage if for any chance a shoot-through current happens. Okay, so that is one thing to consider. The other thing is what happens now if both PNPs turn on and both NPNs go off, right? What happens? Well, clearly the current is going to go through this cycle, right? But what's the problem? The problem is it can go through both of them, because if you look here, it can go like this or it can go like this. Okay? They are very similar. There is no preference between them, so the current can go both ways. And when the current go both ways, no net current will pass through the armatures of the DC motor, so the DC motor will break. Okay, and this is called dynamic braking. So if you want to apply a dynamic brake on a DC motor, you can basically turn both of the PNPs on and both of the NPNs off, and that is enough to stop it. Okay, so keep that in mind. Dynamic braking, shoot through current, and reversal of directions for edge bridges. Now, as I said, these days, mostly as opposed to using a simple chip for an edge bridge, we use a driver. And driver allows you to do both edge bridge and PWM. And the one that I want to talk about in this video is called L298N Motor Driver, which is very common. You can buy it on Amazon for a few bucks. And it does the job of two motors. You see one here and one here. And it can also control a bipolar stepper motor. We'll talk about the stepper motors in the future video. By the way, the pictures that you see from this point downward, they are coming from this website, okay? So the pictures there and these pictures that I had for edge bridge, again, they are coming from my mechatronics textbook, which is Introduction to Mechatronics, designed by Carrier et al., right? He and his colleagues. So the credit goes to these people. I'm just explaining the material. Okay, so going here, if you want to know a little bit about this motor driver, this guy, if you look at it, in general, it has 11 pins. And if you look at them, you have basically 6 pins here, where these 4 in the middle, if you look at them, these 4 in the middle are N1 and N2, so the 2 ones on the left, these 2. These are, let me see if I can use a better color here, maybe blue. So this one and this one, if you can see them, they are N1 and N2. They are basically the inputs for motor 1, motor on the left side, okay, with output 1 and 2 goes to the motor 1. And then N3 and N4 are for motor B, the one for which the voltages are out 3 and out 4 on the right side. Also, these are just to power it, also to control the speed of it, we have enables. So there is one enable here on the left, which is this guy. And that enable on the left is for motor A. It allows to control the speed of motor A with PWM. And this one on the right is enable for motor B. Okay, so these are some of the pins. So 2 out, 2 out. These are 4 outs, and then there are basically 6 pins here in the middle. That's 10 really. And then we also have these voltages here. So one is the ground, of course, and then we have VS and VSS. Here we're just going to use VS voltage. What is VS? The pin VS powers the H bridge. Okay, the H bridge itself, in order to operate, it has a bunch of transistors. It needs power. In order to operate, it needs power, and the VS power will basically accept voltages from 5 to 12 volts and will power the H bridge. We also have a VSS here on the right, which is used to control the logic circuitry between that. Then, as I said, out 1 and 2 are for motor A, 3 and 4 are for motor B, and then in 1 and 2 are for the direction of motor A, in 3 and 4 for direction of motor B, and then enable A and enable B are to turn on and off and control the speed of motors A and B with PWM. So here is the circuit that we have in this system. Okay, let me move this out of the way so you can see the circuit. Okay, so you see that I'm using the B side, and the outs 3 and 4 are connected to the motor, and then I'm using a 12 volt power supply here that you can see up there, right? And then of course I have my Arduino. Pin 9 is connected to the enable B, and pin 7 and 8 are connected to in 3 and 4. The VSS is powered through 5 volt of Arduino, and the voltages for VS and ground are coming from the power supply. Again, you see that Arduino's voltage is not going to the driver, it's the power supply voltage, these two lines that are going to the driver. This separate line, this 5 volt, that can come from Arduino. That's fine. That's VSS. Okay, that is just to control the logic circuit. So it's not high current, and it can come from Arduino. But VS, that can go high voltage and high current, you definitely don't want to connect that to Arduino. Okay, and that's all it is in this case. Now, in order to reverse the direction of rotation, you need to have one of the inputs. In this case, it's not 1 and 2, it's 3 and 4, but that's the same thing. You need to have one of the inputs high, the other one low, or the other way. The first one low, the next one high. That reverses the direction of rotation. If you have both of them low or both of them high, the motor is going to go off. Okay, so it kind of acts like an XOR logic. One of them should only be on, not both of them. Okay, but basically this is all it is, and this is this system that you can see here in the back, right? So that is my Arduino here, and then this is my driver. Here I have attached an eraser that is heavy to the motor so you can see the spin of it, because otherwise it spins so fast you cannot see that it reverses direction. I try to make it heavy and reduce the RPM. And these two red and black, these are coming from the power supply, and the 3 pins are powered, as you can see. This one directly from the Arduino, and these other ones are coming from the power supply. One of them is this one of them is this one. And I'm gonna run it, and here is the code that I also copied from the website I showed you. I modified it. That was for 2 motors. I modified it and changed it a little bit to only run 1 motor. And here you can see that the enable pin B is 9, in 3 and 4 are 8 and 7. And then here first we set them as output, and then we first set them to low. So first make sure that everything is off to start. Then I call the function direction control, which shows you a demo of how to reverse the direction. Then I delayed, and this part I commented out because I don't want to show you PWM first, but later I'll also show you how to do the PWM with the speed control. So in the direction control custom function, first you say that writes a high number to analog write. Now, any number between 0 to 255 can be written on it. If you go 255, that is going to go as fast as it can in either forward or backward direction. Okay, and if you go 100, that is going to go a little bit slower. Okay, so here I'm going to go with some medium low speed so we can see that. First, I start with the delay, and then you see on pin 3, I go high. On pin 4, input 4, which is pin 7 here, I'm going to go low. You see one high, one low. It goes in one direction. Then I reverse it. On input 3, I go low. On input 4, I go high. So that should reverse the direction. And finally, I go both of them low, or you can go both of them high to turn off the motor. So what this function does is it rotates for 2 seconds in one direction, another 2 seconds in the other direction, and then 2 seconds off before going back because it is written inside the loop. So first we're going to run this, and then I'm going to show you how to do the speed control function, which basically changes the PWM continuously so it can accelerate and decelerate. So if you look at this one, you go one low, one high, so you go in one direction of rotation. And then in the acceleration, I use a for loop, and I change my duty cycle here. I goes from 50 to 256. I don't start at 0 because it has shown to me that 0 is not even high enough to start this thing spinning. Okay, you need to go a little bit higher than 0 duty cycle for it to start the spinning. So I go from 50 to 256, like 20% as duty cycle to 100%, and increase it one by one. So you're going to see it accelerate. And then next one, I start at the highest duty cycle and go down one by one to 50. So you're going to see it decelerate. And finally, I turn the motor off. Okay, so let's first go ahead and run this portion, which is already uploaded, right? So here we can upload it again. And once it's there, all I need to do is to connect the ground. And that should be good to go. So it is compiled, it is uploaded. So let's go ahead and run here. You see, it went one direction. There we go. And then it went the other direction. Okay, so here we go. Let me power out the Arduino, and I'm gonna send it again one more time. And then we are going to run. So it is compiling on Arduino. It is uploaded, and I put the shaft in the center. So let's go ahead and start. Okay. So you see, in one direction it goes clockwise, then it goes counterclockwise. So that was clockwise. Stop. Now it goes counterclockwise. Stop. And it keeps repeating. Okay, here I have commented out the direction control and uncommented the speed control. And you can see that here I'm going with one direction of motion. First, I start 3 seconds and just running. And then after 3 seconds, I can go ahead and, you know what, let me reduce that. I don't need 3 seconds. I can just go 1 second. And after 1 second, or, you know, just 100. And then this is where I start changing my duty cycle from 50 to 256. And I don't go at 0 duty cycle because that's not enough to even start this load. So I go from 50 to 256, increase it one at a time by some very small delay. And then I go from 255 down to 50, decelerate, and then at the end I turn it off and wait for 5 seconds before I continue. Okay, so here we go, and here I'm gonna upload it so you can see the PWM of this system. There we go. You see here it is accelerating. You can hear the vibrations clearly. Now stopped. Now it should go fast and then slow down. There we go. And then should stay off, and then should repeat this cycle. Okay, so start slow, then go fast and so on. And if you want to see the transitions better, you can change this delay. Instead of 10 milliseconds, make it 100 milliseconds, so you can see the transitions a little bit in slow motion as opposed to doing it super fast, going from one duty cycle to the next. It just makes the system a little bit slower, so you can see the transitions better. Let's see here. There we go. Stop, and then you go high to low, and finally you go what? You go completely off. Now, of course, there's extra delays because you are doing 100 millisecond delay over 200 numbers changed. That means a lot of delay. That's why 100 is such a big number. Okay, so hopefully you learned something from this video. I'm just telling you that this motor is very, very hot at this moment. Okay, and as I told you, these DC motors are not really meant for long run with high voltage. Even though I'm still doing PWM, still making it very hot. So just keep in mind that if you want to go full duty cycle and go with high voltage, you are going to burn the armature. And here I'm running it with 12 volts. These guys typically should not go as high as 12 volts. It's better to run these at like 9 volts or 6 volts or something. Typically, these are at max at 6. So I guess I'm really putting too much pressure on this, and it's not a good idea. Okay, I just wanted you to see better because I put a big load on it. So here is the final code, and I'm going to allow you to download this under video description. Thank you so much, and I'll see you in the next video.